draw your attention. Uh, yeah, just for like 20 minutes, maybe 20-25 minutes. Okay, so we were discussing about the genetic algorithm. This is part of the local search. And since this is a local, remember in the last class, half of the class, we already covered the genetic algorithm. What about the class test on this upcoming Friday? That we will discuss or I will declare later at the end of the class. Right. So again, what is the motivation of the genetic algorithm? Just like the local search, this is a very efficient search. You will find a good enough solution in a fast enough way. So good enough means a very quick solution. You will find the solution very quickly, and the solution quality will be quite good. I mean near to the optimal solution. Yeah, so just like the local search, the disadvantage is this doesn't guarantee you the optimal solution. That's it. Yeah, so even though this is a local search, but the philosophy or the style of the search is a little bit different compared to the conventional local search like that we have covered, like the simulated annealing, taboo search, and other basic local search, the destroy and repair formula. But here, this is not actually the destroy and repair, rather, it again starts from a random solution, but without any single solution. It starts with a big number of solutions and then try to merge those solutions to get a better solution. So let me talk with the terminologies of this genetic algorithm. Okay, so here basically there are four terminologies as we have discussed. One is the chromosome, gene, allele, and the population. Can you see my screen?
Yes, sir.
Yeah, okay. So we have already covered this, what is what. So let me directly go to the process of the genetic algorithm. As I told you, there are basically three steps. One is the selection process, two is the crossover, and three is the mutation. So let's start, even though I explained this whole thing, but let me give a very quick recap of what is selection, then crossover, then mutation. So first of all, we will start with a not one single random solutions, rather we will start with a collection of solutions, means a population. Say for example, remember what is, okay, so let me clarify again. What is a chromosome? Chromosome is nothing but a single solution. What is population? Population is nothing but a set of chromosome, means a set of solution. What is gene? A gene, in our terminology, we call it variable, but here, or the container, but here they call it gene. And the allele is nothing but the value inside the variable. That's it. So, for example, in the context of these settings of the or the 8-queen problem, so this is the chromosome or the solution. Here we can see that in the first gene, the value is 6. Second gene, value is 7. Third gene, the allele or the value is 2. And this way it continues. And why this is, wow, I mean, how come this value? So this 6 means 1, 2, 3, 4, 5, 6. So this queen is the location of the first queen. I mean the column number 1, the queen number 1. The location of the queen number 1 is at row 6. That's why this is 6. The queen number 2 is at 7. Queen number 3 is at location 2. Location 2 means at row 2. So this way, we cannot keep the pictorial view. We have to represent in a genetic way. And what is the genetic way? The genetic way is a genetic array. We have to present it in an array format. Okay, so that's why this is 672475888. So this is basically the solution. This is basically the chromosome. Okay, so in this case, we have four chromosome. Chromosome number 1, chromosome number 2, 3, and 4. Now, the first thing is we have to go for the selection process. And in order to, selection means selection. Just like in a tournament, we have to select the top players for um, just like a team setup. Yeah, I mean there are 20, 30, 50 participants, but we need to form a team of 11. So we have to select the 11 players. So just like that, there could have many solutions, but we have to concise the solution. We have to take only a few number of solutions. That's why this is called the Darwin's theory. So that means only the survival. This is, uh, I mean, who will be the survival? Only the fit people will be the survival. So survival for the fittest, right? So in order to do the selection, we first need to calculate the fitness. What is the fitness of the solution? So solution number one, the fitness is 24. How we calculate? Because in that settings or in that solution or that chromosome or solution, whatever you say, the total number of non-conflicted pair is 24. So remember, there are total 28 pairs. So out of 28 pairs, 24 pairs are in non-conflicted, or there is no conflict. Non-conflicted pair is 24. So that means that is the highest non-conflicted pair. That's why their fitness is the highest fitness, the solution number one. Solution number two is 23 non-conflicted pair. Solution three, 20, and the last one is 11. So among these, we can remove the second two because their quality is not good, means the fitness is not good. We can keep only the solution number one and two. But well, I mean, if you think the since the third solution is not that bad, so we are still keeping that solution. Well, it doesn't matter if you can take two, you can take three, even you can take all four. So it doesn't matter. I mean, we'll come later in detail about the selection process. There are there are a number of selection process. Okay. So this is just a very quick overview of the complete genetic algorithm process of the genetic algorithm. So what we are doing, we are removing the lowest quality or the lowest fitness solution of the chromosome. And remember how come the 31%, 29%? This is just like 24 divided by 24 plus 23. So the calculation is here, right? So 24 divided by 24 plus 23 plus 20 plus 11. So out of the total number of non-conflicted pair, the solution one has 24. So this is 31%. So that's why this way the percentage is calculated. But anyway, so now we want to discard the fourth solution of the chromosome. We want to keep only the first three. So that is the selection process. So only they are survived 24, 23, and 20. So we want to keep a benchmark of 20. So how, sir, why 20? Why not 18? Why? It depends upon the solution, I mean the application. It varies from application to application. Just for the sake of example, we pick the 20 landmark. So the solution quality or the fitness has to be above 20 or equal to 20. Okay, now there are three. So there are three chromosome, and we need to. I mean, they will be the parent of their children, future children. And how the children will be produced using the crossover. So remember, there will be for every crossover there will be two parents only. So this is the first two parent. So among these three, we have to pick any two for the crossover. So I mean, we can do these two, or these two, or the first one and the third one. Again, it doesn't matter. But yes, I mean, it depends upon the application. I mean, again, if you think, just like this example, if you think you can make a crossover point and you are thinking that the first part of the first solution, the left part of the first chromosome or the solution, and the second part of the second right solution, if we merge these two, then the ultimate child will be this one, and overall the quality of the solution will be better. So then do this. So this crossover point is selected based on the situation, based on the application, based on the demand of the problem. So for example, here we took two solution, and here we pick two solutions. So these two solutions are called the parent one and parent two. So this is parent one and this is parent two. And similarly, there is parent 3 and parent 4. Remember, um, I mean, here one solution is we are taking the same solution to, I mean, the parent 3 and the parent 1 is the same solution basically. But since we need two parents to produce the children, that's why the parent number 1, sorry, I mean, this solution, we are picking this solution for double crossover. So it's okay. I mean, what we are doing, we are crossover these two and also we are crossover with these two. So again, why we choose these things? Again, it depends. This is just for an example. Okay, so how we do the crossover? We make a crossover point and then just we alter. We alter with these two and alter with these two, and you can see this alter. And now this is the new child from this parent, and there is another child. So this is child number 1 and this is child number 2. So we got two children. Similarly, from these two parents, the bottom two parents, we get again two children. There is child number 3 and child number 4. So they are becoming the new generation, and this process will be repeated. We will pick, we will calculate their fitness for selection process, and the high quality solutions will be selected, and the bad quality solutions will be removed. And this process will continue. That's it. But what about the mutation? What is called the mutation? So after the crossover, you see from the crossover, if you pick a child, if you think, if you can change an allele, means a value, means a value of a container. For example, for example, say if you consider, say this, for example, the queen number 6. So this is the queen number 6. So this queen number 6, the value of the queen number 6, or in the genetic term, the allele of the gene 6, allele of the gene 6 is 5. And that 5, that queen is very much responsible for too many conflicts. I mean, it is the main criminal. It's the main criminal. I mean, this queen is creating so many conflict. If you see such things, then what we can do, we can update this content, means this allele, with a new value so that the overall conflict can be reduced drastically. I mean, just a small fragment of change is called a mutation. That's it. It's not a drastic change, just a change in the allele. Yeah, just for example, here that is 327. It could be the case that this 7 means the gene number 3 or queen number 3, and the allele is 7, the value is 7. This 7 is creating some conflicts with some diagonal or row conflicts. This is associated with many conflicts. So if you update this one with 2, now the conflicts are getting reduced. Now the column, I mean, maybe the diagonal conflicts are reduced. And remember, it is not necessary to be always change, I mean, do the mutation only the bad queens. I mean, the responsible or the conflicted queen, who is the most culprit queen. Usually we tune the most culprit queen or the culprit variable or the most conflicted queen, whatever you say. But sometimes we can also change the value of a good queen. I told you before, uh, this could be the case. In the last class, I told you that sometimes a good quality solution could have a minor issue, and that minor issue is transmitted generation after generation. So sometimes this could be a good idea to, even we can pick a good solution and we can change a small fragment if necessary to for the future, then we can do this thing. So in short, mutation is nothing but changing a small fragment, changing the allele rather than changing as a whole. That's it. Changing as a whole is actually done by the crossover. So crossover is totally taking some portion of the parents using the crossover process. So hope you understood, but I will go a little more detail uh, on each of the three process: selection, crossover, and mutation. Let us go through one by one. Let's start with the selection process. Now I will show you some of the selection process. But remember, this is not a very specific algorithm. Again, an idea of the algorithm, not a very specific algorithm. So let's start. Remember, we start with the selection. We'll cover the three process: selection, crossover, and mutation. So let's start with selection. So the first process, the first idea or the algorithm could be this roulette wheel selection. So what is this? You can see, hopefully you are familiar with this picture. So yeah, there is a wheel and there is a bar here, and we have to spin the wheel, and at some time the wheel will stop, and the segment where the point is pointing after it stopped, that will be the winner. So this way we do the selection process. Let me clarify. For example, we have picked six solution. Solution A, B, C, D, E, F, and their respective fitness value you can see at the side. The corresponding fitness value is given. Now, um, place this fitness into this wheel. So hope you can understand that some solution like A is taking a very big chunk of the wheel because its fitness is high. It's 8.2. But the solution with a low fitness, for example, the D. So this is D. So D is taking a very small fragment of the wheel, and that is 1.2. So this way they are occupying different regions of the wheel. And now after after creating this wheel, and now we will pick a fixed point, and now we'll spin the wheel, and it will rotate and rotate. It will continue the rotation. It will continue the rotation, and when it will stop, the point, the solution that is pointed by the pointer will be the winner. Winner means that will be the parent number one. And we'll do it again. The next winner will be the parent number one. And then we will go for the crossover. So how we do the selection? Based on this roulette wheel. And this is called the selection process. So it's a bit funny. It looks like funny, but that is it. This is a very important message is there. There are two important messages. First of all, hope you understand the high quality solution has a high reason and the high probability of winning, right? So with the probability theory, this is a high chance of the high quality solution to be the parent, to be the winner, to go for the crossover compared to the low quality solutions. But why not you are taking the highest two? Who can answer? So the highest value is 8.2 and the second highest is 4.2. So why we are not taking the 8.2 and 4.2? Who can answer?
So because their solution might overlap, so we get nothing new from them.
Uh, Not really. I mean, I told you before, yeah, that's a good answer. But yeah, I mean, actually, I as I've just told you that always good parents, I mean, two best parents might not produce a best child. Sometimes there should have a mix with the low quality parent. I mean, sometimes we should also look for a low quality parent. Low quality means low fitness parent. Since always the good parents are not good for producing good child. That's very important. But The good thing is that is not happening frequently, because high probability, high winning possibility, but low, very, for example, the winning possibility of D is very, very low. So rarely it will win. But by any chance, if it wins, so anyway, I mean, in short, this is nothing but a randomness. This is nothing but a randomness. In AI, in algorithm, in probability theory, randomness is amazing. I mean, randomness is the one of the key to success of the algorithm for finding a good quality solution, for finding even an optimal solution. So randomness is always good. I told you before, even in the last few classes, I'm repeatedly telling you that um, if you are stuck with something, then restart. So the restart will create you or push you to a new random environment. And from that random place, you can continue the previous process. So what I'm saying here, high quality solution or high fitness solution will win in general, but sometimes due to this roll it wheel selection, a low quality, a low probability, sorry, a low quality solution might get enter into act as a parent, and that low quality solution, even though that is low quality, but there could have something interesting that might be helpful for finding a even better quality child. Hope you understand. So I told you in the last class with a uh, different example, might not be practical, but well, I mean, as I told you that, well, for example, there are two-person, and we want to take the best of two, but one person has everything is good, both of them has everything is good, but one person has something negative, and that is very small fraction, but every time the new child or the new generation, they are taking the negative things every time. So how we could avoid that? Just get rid of that parent number two or the parent number whatever, I mean, just change the parent. Take another low quality parent whose other quality is bad, but that quality which was bad by the top quality parent is good for the other parent number three, for example, by parent number four. So take that parent and do the crossover, and you'll get in. If there is a high possibility of getting a good, I mean, get rid of that of that error that is happening again and again. So hope you understand. So in short, there are two messages. One, high quality solution will generally win as a parent, but low quality solution, due to the probability, due to the randomness, they have the chance. They have the chance to get to enter into the parent into the crossover process. So this way we have the we can break the tie, we can break the conventions, and we can reach the we can get rid of the local minima. So this is called the Rowley-Twill selection. Now the second process of the selection, another idea, is the tournament selection. This is the selection process number two. So when we should use it? When there are so many chromosomes that, yeah, I mean, if there are many solutions, what we can do from the chromosome or the solution, just randomly pick a subset. For example, we pick three, a random three solution. So this is the A, E, and T. And now from these three solution, pick the best one. And this will be the parent number one. Similarly, go for the second iteration. Again, from the existing population, means the set of chromosome, pick another three. I mean, the parent already winner. Without that parent, pick another three. And from that three, again, pick that three randomly, okay? And then from that three contestant, just pick the best parent. So remember, from here, A, E, and T, the highest fitness is A, and that's why A wins. So for example, in the next, there is, say, B, C, and T. So among these, we have to check the fitness. If the fitness C has the highest fitness, then we will take C as the parent number two. And then we will go for the crossover. Hope you understand the tournament selection. That's it. Number three, selection process, rank selection. Well, I mean, this is nothing fancy, very simple. Usually, in this case, all the solution has nearly the same quality fitness. You see, the fitness is almost same. So in that case, nothing to do, just go for randomness. This is called the rank selection. Just go for randomness. I mean, or by rank, just take the first two. That's it. I mean, there is nothing because all have the good quality solution. All are the similar, not good, sorry. All have the similar quality fitness. So it's very difficult to choose. So that's all from the selection process. The second is the crossover. So I told you there are three things: selection, crossover, and mutation. So selection is done. Now crossover. So how the parents can do the crossover? What is the crossover process? So one idea is one point crossover. What is one point crossover? Just select a point, just like this. Select a point, and now after select, so how could we select that point? I mean, again, that depends upon problem to problem. It could be the case that this part is very bad. I mean, the second part of the first solution is bad, and the first part of the second solution is the bad. So what we could do, I mean, sometimes these two bad solutions can form a good solution, good child, and the other good subset of the solution they will producing the another child, and maybe in this case the child one and the child two, both of them are good quality than the previous parents. So this is called the crossover one point. So the here the main thing is we will select one point crossover. I mean, there will be only one point crossover. I mean, the both the array both the genetic array should be divided into two parts based on the same point. So here the point is point number 1, 2, 3, 4, 5. In fifth position, we will create a vertical line, and that will be the crossover point. This is called the one point crossover. And now the second one is the multi-point crossover. As the name implies, multi-point. So can you hear me? Hello?
Yes, sir.
Okay.
Yes, sir.
So what is multi-point crossover? We are almost done. Multi-point crossover. Just instead of single point, we will pick 2 points. So here you can see 1 point and there is 2 point. And this is called multi-point. And how we do the crossover? Just take the first one. So pick this one. Sorry, the first portion from the parent one. From the parent two, will the second portion. So this is partition one, partition two, and partition three. So from the partition one will be taken from parent one, partition two from parent two, partition three from parent one. So just like this, and you can see this 1 0 1 2 4 2 3 and 7 8 9 6 7 8 9. So alternatively, okay, and this in total they form the child one, and the other will be from the child two. This is just like the multi-point crossover. Sometimes, I mean, we just need to know the terminologies. Okay, sometimes in the genetic algorithm these type of things are happening very frequently. Well, I mean, there in the literature you will find we have to do the multi-point crossover or one-point crossover or arithmetic crossover. So what does it mean? Hope at that time you'll understand. Oh, I see. So multi-point crossover means there are 2 points by which they are alternatively selecting the first portion of the parent one. The second portion is from the parent two. Third portion is again from the parent one. So this is the alternative selection process for the crossover. That's it. This is called the multi-point crossover. Uniform crossover is very, I mean, something like the multi-point crossover. This is just like gene by gene. For example, for example, in order to produce the child number one, just like this, pick the first one from parent one, second from the parent two, third from the parent one, fourth from the parent. So just like this, one one from parent one, other from parent two. Third gene from parent one, fourth gene from parent two. So this way you form the child number one, just one by one, or you can do two by two, something like. So this is like, so that's why I say this is something like the multi-point crossover. So these two, and then the second two from the child parent two. Then the third, I mean the third two from parent one, fourth two from the parent two, and this way you can pick. Yeah, I mean, even though the example is little bit different than what I'm saying, but actually the uniform crossover is actually uniform way. I mean, the doing the crossover in a uniform way, 1 1 1 1 or 2 2 2 2, something like that. Is something like the almost similar like the multi-point crossover. And lastly, the arithmetic crossover. So sometimes for doing the crossover, we choose some arithmetic formula like AND or XOR, mostly while we are using the binary chromosome. Binary means where the chromosomes are formed with 0 1, 0 1 0 1 0 1 1 1 0 1, something like. So hope you can see the parent one with a binary chromosome, means binary solution. Here is also another binary solutions, and now they are doing the crossover, and new child is produced with the AND operation. So it could be the OR operation, could be an XOR operation. So again, it depends upon the application. So I mean, well, I mean, yeah, I mean, of course there should have some reason, but yeah, sometimes we need to do some arithmetic type crossover, and that is called the arithmetic crossover. Hope you understand. I mean, some arithmetic operations are happening here. So lastly, the mutation. The third part of the overall process is called the mutation. And now I would like to end up with some mutation process. So mutation number one, idea number one is called the bit flip mutation. Again, usually for the binary chromosome. So for example, bit flip mutation. So for example, in the gene number 4, the allele is 1, means the in variable 4 or queen 4 or variable 4, whatever you say, the value is 1. So what is bit flip? Bit flip means we'll flip it. If it is 1, we'll make it 0. If it is 0, we'll make it 1. So that is, remember, what is mutation? Mutation is just take a gene or any random, is not random, take a variable, maybe mostly the most conflicted variable, and take the gene, or sorry, take the allele or the value and just flip it, and that is called the bit flip. So, sir, what about the n queen? So, for example, if n queen, if the value is 2, you can make it 6. It's like a flip, right? I mean, just mirroring. If it is in row number 2, if you mirror it, then it will go to the row number 6. Row number 1, row number 8. Row number 2, sorry, row number 2 means row number 7. Sorry, yes. So it's like 1, 2, 3, 4, 5, 6, 7, 8. So if we flip 2, then it will go to 7. So if we flip 3, then it will go to 6. If we flip 4, then it will go to 5. So it's like a flipping. So yeah, I mean, this is called the bit flip mutation. I'm not covering the random resetting. I mean, randomness is random, nothing to say. Swap mutation. What is swap mutation? The another idea of the mutation, swap mutation. So in that case, you will take two gene, you will pick two gene, means two conflicted gene, or two um, um, for example, the queen, if you pick two queens who are very much in conflict, and then the swap mutation says just swap the values or swap the allele of the two gene. I mean, 2 will go here, 6 will come here. So just like this. So you see the change here. The 6 is now here and the 2 is now there. I mean, they are just swapping each other. And that is called the swap mutation. But the ultimate purpose is with this single swap, a big number of conflicts has been reduced, and that is called a mutation and a swap mutation. And last two is the scramble mutation and inverse mutation. What is scramble mutation? Well, this is against the points I have explained. It's not a small change. Sometimes, for example, if you have a chromosome of 1,000 arrays, 1,000 elements, or 1,000 genes, just pick some uh, I mean, just choose a subset which are usually very in conflict situation, and then, for example, these genes are very much in conflict. I mean, they are all in total, they are creating many conflicts. Yeah, they are the conflicted genes. So what we could do, we can randomly shuffle these genes. So just do the shuffling or the scrambling. So after the scrambling, you can see now the 1, 2, 3, 4, 5, 6 is now scrambled. So it's like just shuffled, just 2, 5, 3, 6, 4, 5, etc. And the ultimate, so this was the child one, and this is the child one hash. Means that child one has been reformed after the mutation, and that is called the scrambled mutation. And finally, the inverse mutation again is something like scrambled, but well, this is just the reverse. I mean, like, yeah, I mean, for example, again, this is the subset of the child, say child 5, and possibly they are in conflict. They are creating too much conflict. And what we can do, rather than scrambling, we can just reverse the order. So 2 will go to 6. So it's like 2, 3, 4, 5, 6. And now we'll write 6, 5, 4, 3, 2. And just is getting reversed, I mean inversed. And that's it. And that is called inverse mutation. So what we have learned, already done, we have learned the overall genetic algorithm, the process of the genetic algorithm, and mostly, in a big picture, the process is, we'll start with the three main phases: selection, crossover, and mutation. But before the selection, we need to do the fitness. And based on the fitness, we do the selection process. And before the crossover, we need to find the pair. Which pair of parents will go for crossover? And after the crossover, we go for mutation. Mutation is nothing but a small change in the genes. Some of the genes are need to be changed. I mean, their values or alleles need to be changed before going for the next iteration. And what is the next iteration? Again, from the mutation, go for the selection. And it will continue repeating. It will be repeated for some iterations, and eventually you will end up with a very good quality children or the solutions. That's all for today. Any question?